Hi, I'm DJ Ware. On this episode of the CyberGizmo, we're going to be looking at multi-core architectures for Linux right after this. So I guess the biggest question when we're talking about getting into some of the performance aspects of Linux is how does Linux manage processes and threads? But more importantly, what is a process and what is a thread on multi-core machines? How does all that work? Because you really need, if you're going to do much in performance tuning, you really need to understand this first. Otherwise, you may affect your systems in ways that actually degrade performance. So let's avoid that. Let's talk about first some of the. This would be the last single-core CPU that I remember was the Pentium 4, and basically they were designed with a single core, and everything, all the execution went through that one core. But they're pretty much, even the multi-core designs are all based on similar block architecture. To the single core, there's just more of them. But they all have a register file that's used to manage, pushing data into the arithmetic logic unit or the ALU to do an addition or subtraction or multiplication or division. Now, ALUs today contain more than just those 4 instructions, but those are the basic types, those 4. The chip also has some method for interfacing with a bus, and that would then talk to either an I/O bridge or to a memory bus to talk to main memory. The I/O bridge is used to interface to like a USB controller, your graphics card, your disk controller. That can be on your motherboard, like the inbuilt SATA controller, or it can be an external card, which is on your PCI bus, like a SAS or a RAID controller. And then you have additional expansion slots for NVMe and all those kinds of things, which can interface that type of I/O to your machine. And then once you get into multi-core, you just replicate the chip side of that, sharing the same bus. So there's additional logic, if you will, on or firm or microcode that's on the CPU that manages the bus so it gets shared properly without an overlap or collision between the multiple CPUs. So all the CPU cores fit on the same die. So yeah, you can have like in the early days you had dual core. You still have dual core machines that are around. You also have quad core, and those are still around today. And you have hexacore or 6-core, and you have octa-core or 8-core, and on up to 16 and 32 and 64, and probably not too much longer, 128 and 256 core. Those were also known as chip multiprocessor, or CMPs. You don't really hear that term too much today, CMPs. Most people just call them multi-core, or they call them octa-core, or they call them quad-core, whatever the actual number of core count is. But the main thing to take away from this is that all the cores run in parallel. It's true parallelism between the cores. The processes and threads run simultaneously on those cores. And if a process or a thread is running on one of the cores, then Linux will manage them in a time slice. So it'll give this thread this much time, and then it'll bring the next thread in to run, and then it'll give it that much time, and so forth. So if it's running on a single core out of that multi-core CPU, it time slices it. But as far as running it across the cores, it just manages them in parallel. So interaction of between the multi-CPU and Linux. Linux just looks at it as a bunch of CPUs on the same board. It doesn't look at it as a multi-core, although is some logic in there that understands multi-core. And then the Linux scheduler maps threads and processes to those different cores. And by the way, if you are running the soft threads, or what the BIOS refers to as threads, and say you had a quad core and then you turn hyperthreading on, then you would have 8 cores. Linux perceives that as 8 different machines. So yeah, and Windows and Mac do the same thing. They have similar things, not quite the same, but they They do manage in a similar vein. They do manage the processes in a similar vein. So a process, what is it? It's a complete application. Say like the ls command, or it could be the file manager on your desktop. So that would be a complete process. That would be assigned by the Linux scheduler a PID, or a process ID. And so if you're looking at top or you're looking at HTOP, you'll see a PID, a PID number, or it might even be, might just be shortened to ID. But that is the process ID number that the Linux machine is using to manage that particular application during its lifetime. So the time it starts executing until the time that you're finished with it. So each time you execute an application, you get a new process ID. And that can either be from the menu or the command line. The way Linux does that is it creates a fork. And that is, it will allocate a portion of memory. It basically forks that off, and then will load in your application into that space. Your application will then allocate its resources, its private memory and its public memory that it's using. Also, it will allocate a little bit of space for housekeeping, and that's for the Linux scheduler to be, and the Linux kernel to be able to manage state on your application, whether it's stopped or sleeping or waiting for I/O or something like that, or running as well. A thread, in computer science, a thread is really a shortened nomenclature for thread of execution. Threads are quite a bit different than a process, because a thread is actually, it's not forked, it's not a copy of the process, it is a split. So you can take portions of your code that you want to run in multi-thread, and you can split them into 2 or 3 or 4, however many you want. And that allows for those particular pieces to run simultaneously from the main body of the process code. So it's basically like if you were doing a bunch of I/O reads on different files, you could split a thread to read, those different files, or you could split a read so that some of it reads the first 10 blocks of data, the next one reads 10 through 20, and then 21 through 30. Something like that, you can use that for threading so that you get some gain in parallelism from the execution through the threads to get the data loaded up quicker. But essentially, a thread is really a shortcut to parallelism. It has a lot less overhead. If you were to sit down and actually write a parallel piece of code, you would be head scratching a lot. It is not an easy job to do. And threads were a shortcut. They allowed us to get to parallelism quicker. So, but threads are lightweight. They're lighter weight than a process. You can certainly fork a process into 2 and have it work on different parts of the system. But you're bringing in the entire code base to do that. So threads don't do that. They only allocate the amount of memory that they are required to do for that section of code that is multi-threaded. Hope that made sense. Memory in multi-core has to be managed differently, of course, because one, we have to protect memory from being read by some other application that isn't authorized to get to it. And second, we have to prevent an application from writing into some other process's memory that it's using. In either case, that would be a bad thing. So we manage it between the multiple CPUs, and if your motherboard supports multiple chips on the same motherboard, so the memory would be managed, if it was on a single chip, would be managed by some kind of memory bus. If it was, if you had 2 CPUs, physical CPUs on the same motherboard, then there would be some kind of connection or some kind of fabric that allows those 2 chips to communicate, because on most of them, the memory is allocated to the chip. So I would have a block of memory on. If I had a picture here, I could probably show you, but I don't. So the blocks of memory are actually physically allocated to the chip. So there's a block of memory to the right or left of one of the CPUs, and then there's a block of memory or sockets also installed on the other side. So memory installed in those are actually owned by the CPU, and there has to be some fabric to allow them to communicate. In Intel, it's called Quick Path, and that allows one CPU to tell the other CPU, hey, I need some memory that you're managing, and then the other CPU would act as a proxy so that it can gain access to that memory. And that is called shared memory. You can have shared memory within the CPU, or you can have shared memory across multiple CPUs. There's also something called distributed memory, and this is a little bit confusing that they use this term distributed, because to me, distributed memory would be used between physical pieces of hardware, physical machines, that would allow me to share memory across that, but that's not what it's talking about here. Shared memory in this construct would be like your level 1 cache. It's private memory. So it's memory that is not replicated anywhere else. It's memory that's private to that particular CPU. And so, yeah, it's, I don't know why they didn't just go, why do you call it private memory? Yeah, distributed memory is generally either L1 or L2 or both. It depends on how the chip manufacturer designed their L2 cache. Some L2, we'll get into that. So how does Linux manage threads? So Linux manages threads through something called the simultaneous multi-threading, or SMIT. SMIT provides independent thread execution simultaneously on the same core, but there is some rules. So SMIT weaves together these threads on the same core so that they appear to have some kind of execution that's occurring simultaneously. But threads cannot run on the same parts of the CPU. So for example, if and this is only true of SMIT. So if I have a thread that is using the floating point, part of the ALU, and I have a thread that is using the integer part of the ALU, those two threads can run together. They can run simultaneously. But if I have a thread that is using floating point and another thread that's using floating point, then only one of those can run at a time. Same with the integer. If I have two threads using integer, only one of those can run at a time. Without SMIT, the execution of the threads would be one at a time. So, yeah, it's kind of an early thing that came about through the motherboard manufacturers and also the chip manufacturers. It's still around. However, multi-cores versus SMIT, each core is smaller, and the more cores your CPU has, the slower the clock rate. So that's to manage the heat dissipation as well as the power requirements for the CPU. Because the more cores you have, the more parallelism you have, and the more things that your CPU die is doing. And so they clock down usually they clock down the clock rate in order to control the heat and power requirements. However, multi-core is better at parallelism than SMIT is, because it offers true parallelism. SMIT was originally designed for large and fast superscalar cores. That goes back to the Pentium 3, the Pentium 4. So yeah, it was a way to use single core and allow threads to execute on the single core. They offer greater performance on a single thread than multi-cores do. However, they don't offer true parallelism, because they will block if once they're accessing the resource, they will block that resource from another thread from using it. So, yeah, I mean, it's another tool in the box, right? Another tool in the box. So multi-core, multi-threading, in order for this to work, all the caches have to be shared. So we have to have one cache someplace that is shared. L1 isn't the place to do that, because that's private memory, always, as far as I have ever seen. I've never seen shared memory out of L1 in my memory. But L2, and that depends on the chip manufacturer, L2, L3. Though L2 can be either private or it can be shared. It depends on the hardware implementation of it. L3 would be shared, and of course memory is always shared. And then there's also L4, which is disk, or L5. So yeah, memory is always going to be shared. So the worst case scenario is you'd use shared memory constructs. The killer. Context switches. Context switches occur whenever Linux needs to roll your application out, do a page, need to change out the page, the code pages, or it needs to stop your application because another high priority application has come in and is demanding resources that your application is using. So context switches can occur at any time. There's no set schedule for those to occur at all. So what the bottom line is that the Linux scheduler might need to move your code to another CPU. And so when that happens, we get a lot of overhead. First of all the caches that your program was using or your thread was using get dumped, get thrown out. The execution pipeline gets cleared. The state of your process gets saved, and the OS then stops you. It will then do a fork on the new code. It'll load your processes back in. It'll restore the state. It'll rebuild the caches from your system code. There's no magic that occurs here. It's not saving. It's not pulling the caches across from the other machine. And then as your program executes, you then refresh and rebuild up your execution pipeline. So in short, a context switch across processors is a killer. It's a killer of performance. So how does Linux manage that? So Linux tries to minimize context switches for an application or a thread. It has an affinity mask that it uses to control where your code is running. And the other thing is the affinity mask is inherited from the parent. So whatever spawned you, whether it be the Linux scheduler or whether it was a process that performed a fork, whatever that affinity mask was, you get that as default. So what is an affinity mask? It is a way of telling what the cores a process or a thread can execute on, and it's read from right to left. So if I had 1101 as an affinity mask, that would mean that core 0 would have a 1, core 2 would have a 1, and core 3 would have a 1. And core 1 would have a 0. So in this case, what that means is that this thread or process can run on core 3, core 2, and core 0, but it cannot run on core 1. We're blocking it from running on core 1. So the rules are the Linux scheduler prefers to keep processes and threads on the same core in which they were initially, in which the initial execution began. That's called soft affinity. Yes, Linux scheduler can change its mind, and that's why it's called soft, and that depends on the system load and the priority of other applications that are running in your space. A developer, however, can specify their own affinity, and that's called a hard affinity. It cannot change unless there is a command within the application to change it. So yeah, once you've changed the affinity to hard, it remains that until another command changes it. If you're doing this with applications that are currently running, you can use the task set command to do that. And task set does a lot of different things. So the one we're concerned about here is the option -PC, and P is for the process ID and C is for the core. So you have to know the PID number of the process that you want to change the affinity for, and then you just give it the mask for the cores that you want to run it on. And the rule of thumb is generally don't do this. Don't use hard affinity unless you absolutely have an application that requires it. Let Linux do it. It does a pretty good job overall of trying to maintain context switches, trying to prevent context switches across cores. So, but there are times, like there's always some rule that breaks, there's always some exception that breaks the rule. And yes, there are always, there are times when you will want to set affinity. For example, if you have a thread that's sharing data structures in memory, you want to keep those on the same core. Because you don't want to have to rebuild your cache again every time. That's expensive, especially if the cache sizes are really large. Also, if you're using real-time threads, that is, maybe you're controlling a robot or you're controlling an industrial control system or maybe you're in a medical situation in a hospital where you're using real-time processes to control medical equipment. Yeah, you probably are going to want to stick that to a core because you don't want the context switch to interrupt the flow of execution that's going to a real-time task. You could lose clock. I have seen synchronous motors go out of control. Yeah, there's some bad things that can happen. So yeah, there are times where you'll want to set affinity to do that. So in conclusion today, parallel programming is more difficult than using the Linux process thread management system, obviously. And I mean, you could get better well, maybe you could get better parallelism if you wrote your own code to do it, but there is a shortcut, and you can use the thread management and the process management within multi-cores to do that. And by the way, virtualization or Docker or containers, those are also shortcuts to parallelization. SMIT is okay, but it's not as good as multi-core. It's older, but multi-core is definitely better than SMIT, as we've seen. But as we've seen with Spectre, there's always a but, right? But as we see with Spectre Meltdown, there are if we don't clear our caches correctly, it is possible for an application that comes in after yours pick up your cache memory and read your data. And that was one of the original problems with Spectre Meltdown, is that the caches were not being cleared properly. And there are all kinds of variants using the sidechain that are exposing additional ones even now. There's still more coming. I suspect that we're not done quite yet with all that. There's also some things I haven't covered today. There's different types of memory access models. There's the uniform memory access, or UMA. There's also NUMA, which is the non-uniform memory access, and I didn't cover those today. I'll probably do that in a future video, or if you guys want, I'll probably do it in specifics. There's also ways that you can share memory across, say, a Beowulf cluster of Linux machines. So, yeah. So like always, I hope you enjoyed this video today. Affinity is central, and context switches are central to getting good performance out of a machine. Of course, there are other aspects of performance tuning as well. And I'm just trying to lay the groundwork today, if you got this far, to move forward into the performance aspects of Linux. I hope you enjoyed this video. If you did, please like and subscribe. Hope to see you all again real soon. Bye for now.